Thank you so much, sir. Now I take the honor to inviting Dr. Suryakant Gautam, sir, to deliver session 2 of the day. Sir, he is known for his deep expertise in the field of digital system and cyber security. We are truly privileged to learn from his experience today. Sir, over to you.
Good afternoon, everyone. I'm very thankful to Dr. Damodar Tiwari sir for this welcome and Mr. Patil sir. So today we are discussing with respect to fundamentals of cyber physical system. I hope I'm audible. So first we need to understand how this is useful in our daily life and in modern technological innovation domain. So first we will understand what are the concepts behind cyber physical systems. So today I will be discussing with respect to basics of the first cyber physical system, what are the components involved behind cyber physical system, then how we handle input output in a given cyber physical system. Because at the end we need to provide some base for the connection between the physical world. So that will help through the input and output system. Third is how we can design a given physical process. Finally, we need to monitor our physical process, whether it is in any advanced UAV application or highly sophisticated power plant systems. So at time we need to connect with the physical process, and that can be done through the input-output system. Finally, we need to make sure how we are designing the given physical process. One option is model-based design, another is the data-driven design. So we will be discussing both options, how we can handle this. Now, to connect with the physical process, we are looking with the sensors only, and then whatever command we are giving, that to be actuate on the actual physical process. That can be done through the actuators. So this is the next part, and later on I will take few real-time example using the Kalman filter, a specific application for the complex physical domain that is related to nuclear power plant. So here, for any technology, generally it follows some kind of hype curve where we need to understand how it starts. So first, innovation trigger is the main key point behind any technological development. Later on, peak of inflated expectation, as we see in various kind of application with respect to the cyber physical system, and later on, through of disillusionment happen. like whatever we have done as a development from the innovation seed, we realized it is not realizable into the physical domain. So this is the, it passed through the through of delusionment. Later on, we reach to the plateau of productivity. So I have taken a lot of example with respect to the cyber physical system only. So in the hype cycle, it can be seen like a digital twin, now at the peak of inflated expectation, and nowadays it is taking traction. So whenever we are about to reach through a deep disillusionment, so it is possible that we can take forward for the actual product level design. So this hype cycle is really important because sometimes what we take as a lot of learning over the components, technology or innovation as a first subject. But later on we realize it is not actually feasible for our physical domain. So this hype cycle help us to understand when or what time we will be reaching to the plateau of productivity.
स्लाइड नंबर बोलता है गो टू, आपको जिस भी स्लाइड नंबर पे जाना है।
कर दो ना तो इसी में
सर यहाँ से करवा देते हैं
सर, यहाँ से आप बोलते हैं नेक्स्ट कर देंगे। नेक्स्ट
पेन ड्राइव से कर, पेन ड्राइव कहाँ है?
कौन सी वाली साइज में? सी
CPS
नेक्स्ट कर दीजिए।
एक मिनट
राइट लेफ्ट
एक मिनट सर सर एक मिनट इसमें चल जाएगा सर थोड़ा बड़ा कर दो चल जाएगा
next actually Adobe is Adobe सही
एडॉप्ट कोई इसमें नहीं एडॉप्ट
एडोब पे वो रही हूँ
हो जाएगा।
चालू हो गया ना चल
ठीक है सर
next slide please. Yeah. So we need to first understand the cyber physical system architecture. This is important part while designing any kind of cyber physical system. So this term emerged in 2006 itself by National Science Foundation in the USA. It is standardized after this year. So in general, we call cyber physical system is a combination of physical system plus computation plus communication. So for the computation, generally we use the embedded system standalone where algorithm process to the for the physical system, and communication happen between the physical system and computational platform. So in this block diagram, what we can see, it's a general connection between physical interface and sensors and actuators and the computation platform. So here we have considered two platform 1 and platform 2. In platform 1, sensor 1 and computation 1 is happening. Simultaneously for the platform 2, sensor 2 and computation 2 is happening. Now main important point is merging, how we need to merge the information processed in the platform 1 and platform 2. And then this whole merging is actually triggering actuation process through actuator 1, and it is connecting with the physical interface. And then again physical plant and the physical interface for the sensor is taking the value from the actual environment, and then the whole processing happens. So here the objective behind such architecture is because when we look any system, it is not very easy to design at the first sight. Lot of individual components to be taken care by individual team or group of researchers, and for that we need to make sure platforms are selected very carefully, and we need to be merged again because someone is working with the mechanical domain and we are working with the electronics domain, but at the end we need to merge to operate a real physical process. So the merging should be happen very carefully with proper protocols, whatever we have decided in the starting itself. So it's a very simple architecture which involves physical system, computation and communication. Yeah, next. We can also look the few standard definition based on the National Science Foundation of the USA. What is cyber physical system? And because it is engineered system that are built from and depend upon seamless integration of computational or physical components. This is one part. Now, how do we handle development of the any CPS? CPS will enable us for the capability, adaptability, reliability, and scalability. So, as of now, suppose we see a simple train engine. So, there initially it was simple physical process that was operated by the loco pilot. There was no much communication or any physical control over the system. But nowadays we are able to handle controlling from the central position itself, like a fog control, accident control, or any information to be communicated immediately. That so it is possible only by the cyber physical system. So it offers us a lot of scalability and resiliency, and how this technology is getting transformed for the people who interact, like by using the augmented reality and the Internet of Things and the smart manufacturing. So these are the standard definitions that to be followed while designing cyber physical system. Application domain, we are well aware, it can be utilized almost in n number of domains, and it is widely acceptable almost nowadays in every important physical application. It may be energy, biomedical, avionics, military, manufacturing, building, automotive, anywhere. So for the automotive itself, we have one, like if we talk about Bhopal, so in the Bhopal itself there is a one great startup working for the automotive vehicles. Like Tesla is in the world level, but in our India also we have a lot of great startup. So it is totally nowadays cyber based physical system. So these are the major application domain, but we need to make sure three critical parameters in the top itself. It is mentioned cyber plus physical if we are doing the interaction. Second, possible chances of interaction is computational plus dynamics control and plus communication. So here my emphasis is always whenever we choose any system which is to be integrated with the cyber physical format, the combination to be chosen very carefully. For what purpose? If it is for security and safety, then make sure accordingly parameter to be decided. If it is for just computation, dynamics and communication, like just basic control for any input output based control system, then such combination can be taken care. So for the application, we need to make sure what combination, and accordingly we need to design our parameter for further starting point of the any physical system design. Please next. Yes, so this is another interesting story with respect to cyber physical system. Here what happens, suppose if anybody is promoting, let's use the cyber physical system, but another guy within a team will contradict for that, and it is actually happen when we do project based outcome for any institution or any big organization or any company. So these are the contradictions. Someone is ready for the adaptability, but the question may be arise repeatability. So we need to make sure these are the list of contradiction to be taken care very properly before initiating any such kind of project. These are the fundamental concept to be introduced while beginning any cyber physical system to be the production mode. Next is high connectivity versus security and privacy, high performance versus low energy. These are the contradictions, and always these questions will be raised as per the domain application, like asynchrony versus coordination and cooperation, laws and regulation versus technical possibilities. So these factors to be taken care very carefully while designing CPS system. So suppose we have started a project and we have a great team, but these are the fragmented teams. So here the point of this is a very interesting visual metaphor, and if team is getting provoked like some just question, random question, how you perceive given a system. So everybody will have different answer for the cyber physical system. So the point is cyber physical system cannot be seen in the silos. We need to look into the integrated manner whatever we are going to design. So if somebody from a simple network guy, he will always tell nothing in the CPS, it's a network and communication protocol is happening. But if we ask any sensor guy, he will tell it's nothing, it's just we are sensing and providing manipulation, that's it. So all components are having weightage in the CSP. So make sure whenever we are starting design, we need to make sure there should not be any fragmented system. We need to talk into the integrated manner before designing any CSP. So in CSP, every sensor, actuator, communication node, networking link must collaborate to form a cohesive, real-time and physical accurate model for whatever the system we have taken into the consideration. So that is the main objective behind cyber physical system design. So nowadays, this is almost automotive based cyber physical system is reached on the plateau of productivity. Like we see in the USA, Tesla's car are in lot of production domain, and it is a real application of the cyber physical system. Where we are getting in this integration, we are getting safer transportation, reduced emission, smart transportation, energy efficient, climate change. We are handling also through this, and human robot collaboration. So these are the main advantages if we are choosing suppose automotive industry for the cyber physical system. And I have covered this because it is reached in the plateau of productivity instead of innovation or productivity hype anything. This is in the physical domain now, and it is really perceivable by the human being. So it is really advantageous if we use CPS, whatever physical application we perceive as a main motivation. This is another application, Star Mach quadrotor aircraft, and this is also a reality nowadays. So, like in the latest war itself with Iran and Israel, and in the India and Pakistan also, we have seen a lot of application of the drone. So, drone is a great example for this cyber physical system. We are controlling everything from the base station or through satellite, whatever means we have. But here I have detailed out how it is happening in terms of the cyber, physical and the system. So here our physical object is the physical component, drone, that motion to be controlled every way. So for that we have such kind of sensors, LIDAR, stereo cam, GPS, IMU, ranger and ranger. These are just radar type of rangers. So these are first column is providing list of sensors. Now the blue line and the red lines and the double columns, these are providing the communication connection. RS-232 cable, firework and the UART based communication protocol. And these are the PC, Stargate, Robostick, Beacon. These are little like light yellow color. These are our computational platform, what we call embedded system. And finally communication is happening through the Wi-Fi mode. And beacon and the escape and motors, these are the specifically our actuator. So it is a complete block of the sensor, actuation and communication to control a UAV, unmanned air vehicle, if we call in the general. So nowadays these are the reality, and it happens through the seamless integration of the cyber physical system. Okay. So now the question is how we can start for any physical environment in terms of the cyber physical system. For that we need to understand the model, design and analysis at the very beginning itself. So why we need to model? The question is, so the answer is very simple. We need to understand deeper information about the process. Whatever the physical system we are considering, that is to be understood fully, and it can be happen only through the modeling process. Now modeling can be data driven or model driven or knowledge based driven. Okay. So we'll see one by one how we can do the modeling also. Later on, after modeling, a design to be happen, like whatever the model we have thought the structure to be designed. And later on analysis. After structure design, we are assembling the system, then every part or every testing parameter to be analyzed carefully. So these are the three major cycle to complete any physical process to convert into the cyber physical domain. That is modeling, design, analysis. So on the same line, this is the roadmap. Whenever we choose any system for the designing, so it happens through the modeling, then design, then analysis. So in the modeling part, we need to understand the dynamics of the system. Now dynamics can be continuous or discrete. So these are the now integrity come into the picture. Initially whatever we have thought, that was very top level information. But as we moving for the design roadmap, then we need to understand the system in detail. So here in the part of modeling, we need to understand whether it is a continuous dynamics or discrete dynamics or mix of the both hybrid system, or composition of state machine, whether only discrete states are available. And then concurrent models may also happen with the terms of states and continuous dynamics. Second part is design. So after confirming what kind of model to be designed, then only designing can be integrated. Like if we know the dynamics is in the continuous manner, then accordingly we need to choose the sensors and actuators. Embedded system where algorithm will be born, whole system will be controlled, and memory architecture, input output connections, multitasking, whether scheduling, like time synchronization, and with the whole system synchronization. So after modeling, if the design part is also done, then we need to understand the analysis, like how invariant and temporal logic we are designing for a given system what we have chosen. Because at the end, based on the logic, we will be designing our computational platform, and then communication will happen. Now, equivalence and refinement, reachability analysis and model checking, these are the parameters. So on each component we need to focus very carefully, whether first in the model part, then design, and then analysis. And in between we need to go through each connectivity, and accordingly we need to select a suited component. Like if I talk with the sensor, then we need to carefully design sensor, and then how it is to be discretized, and then how to be communicate, means transfer of the data with the embedded system, and then embedded system back provide to the actuator. Actuator will create the actuation for the dynamic model. So the control feedback to be closed, and to close that feedback we should understand in deep whatever the modeling, design and analysis part. The next. So here now I am talking what can be used as computational platform for the cyber physical system. So the like a simple computer we are not considering as an embedded system, but embedded system is a standalone computing platform for the cyber physical system. So here it will include CPU, input output devices, memory, and connection with the analog domain. So embedded system will act as a computational platform for the cyber physical system. So what kind of embedded system we can use nowadays? The next slide. So before that, we also need to take in like these parameters to be considered. How information will flow in between the embedded system and the physical process. Whether like in the cyber I have mentioned, and for the physical. So physical generally happen into the continuum, like continuous in time in any physical process. But cyber, like whatever computation we do, it happens in the digital domain only. Discrete in time and discrete in amplitude value also, and that to be happen sequential or non-sequential, that is separate part. But for the cyber, it is to be taken care. And communication we need to define accordingly, whether wireless or wireless, serial, parallel, how it is to be done, event trigger or normal sampled portion. So these are the major challenges while connecting the computational with the physical world. So these parameters to be taken care accordingly. Yes, so nowadays ARM processor family can be utilized for the computation purpose while integrating any physical world. So there are three family: A family, R family, and M family with respect to the ARM Cortex processor. A family generally used for the application purpose. So in the beginning itself, as I discussed, whatever the physical system we are considering to be converted into the CPS, that is to be taken care very carefully, because accordingly we need to choose the hardware for the computation, and that will create optimized in terms of cost, time, synchronization or scheduling, anything. So A family for the application, R family we need to select for the real-time processing with high performance, M family for the microcontroller or a small robot kind of applications. Yeah, next. So next, latest hardware is available with is the Raspberry Pi 3 model B+. This is the latest available from the Raspberry Pi, and it is a generalized kind of board we can use to design any cyber physical application. So as we can see, there are two USB port and one line port and 40 pin based extended generalized pin input output, and we have this processor, 64-bit quad-core GPU processor, on-board Wi-Fi, Bluetooth, SD card, DSI display board. So these are the kind of generalized component to be used as an embedded system to control any physical process. So this is the latest. Like if we want to design at the lab level or research level project, we can use directly this board as an embedded system, and we can control any physical process using this. We need to just implement our program in Python or MATLAB and then connect through our USB or input-output pin for the interface with the physical one. So this can also be used in the UAV based application like a drone or anti-drone technology. We can use such board also because it is having CSI camera port for connecting a Raspberry Pi camera. So here we can get the signal and whatever information we want to fuse with the existing sensor, we can add this also. Yeah, next. So for the lab level experiment, we can do the similar kind of experiment. Here we have our Raspberry Pi, the connection with the general purpose input-output pins. So 40 pins are there, and there is a breadboard. Like we can play in the lab itself to control any basic example to understand how cyber-physical system interaction happen. So this board is having low cost also, like 15 to 25,000 happen for this Raspberry Pi D Plus model. It is a generalized and it is having a lot of great functionality in terms of embedded system. And it is available for the Python, MATLAB, whatever language we use for the programming language. So why we are preferring this instrument for the basic research or application? Because it operates in the real-time situation also, like reading sensor data and toggling actuator in embedded control part. So it actually creates complete feedback system, where take the sensing information and then create the control signal and provide it to the actuator to create the actuation for a physical plant. So based on this component, we can play around to design any basic cyber physical system. Yeah. Next. So now we'll talk, as I told, first part is model, then design, then analysis. So now we are reaching for the model part. So here, what we are modeling actually, we are trying to model whatever the process we are going to control through the cyber component. Cyber means here computation plus communication. So here, first we need to understand how we are going to model, whether it is a deterministic model or non-deterministic model. But generally, this contradiction happens while designing any physical process. But as of now, we will be talking about deterministic. Later on, we'll reach for the probabilistic modeling also. So in the model, like a simple first block is showing just Newton equations, Newton laws equations that is to be modeled through the differential equation. So what we are doing, Newton's law we are modeling. Newton's law is just observation for the physical process, what is happening. And we need to convert that reality into the model form. So we are using differential equation to model such observation. Second, this is for the big robot balls, small balls within a box here, and this target to be designed. So for this also we need to understand how our any mathematical equation is actually matching with the target. So we need to understand it's a dual process. Like if we know the target, then we need to think for the model build. If we know the basic observation, then we need to understand what will be the target. So it is a two-way flow. So every time we need to take care with the reality and what is actual we are going to be designing. Next please. So like this question happens normally, because if we are choosing deterministic modeling, then any other guy will come from the team and will tell this very important. Like here the question is, you will never strike oil by drilling through the map. It's very plain. But it will not diminish the value of any map. So we need to understand deterministic model will tell the first footprint for the physical process. Later on we can play around whatever the model uncertainty we want to include. So here first is the determinacy. I mean, physical process first need to be determined. Then only we can play with the probabilistic and any other thing. So a model is deterministic if given the initial state and the input, the model defines exactly. Like if we know the initial condition or operating point for any power plant or any system, and we know the set of input, then we can conclude what will be the output. It is a determinism, and it is to be proven through the past data also. So for that we need to do system identification kind of approaches, like where generally in the data sciences we do AR, MR, MA, ARIMA, AirMax kind of processes. Such kind of identification we take care for that. Next. Okay, so in the beginning itself we have seen basic architecture of the cyber physical system. So the same model I have taken. Cyber physical involved computational platform, network fabric, and the computational platform with the physical one. So in the beginning we were talking with the deterministic modeling. So suppose we are able to now understand how model will look like in terms of mathematics. But these are the components involved in the cyber physical system. And these component uncertainty or any kind of probabilistic information to be considered for the final design of the model. Okay. So what are the cases in the network fabric? We can understand the packet loss, non-synchronization, unknown delays, uncontrollable scheduling through the computational platform. In the physical plant, where we can have the uncertainty into the parameter of the plant itself. Okay. Sensor fault, sensor noise, actuator fault, actuator noise, physical noise, unknown noise, like non-deterministic noises, that may happen through the physical process. So that is to be taken care in the next stage. Like uncertainties should also be included in our model design. That is to be the objective in the design part first. Yeah, next. So now again the question is what kind of models are useful? Whether it is deterministic or it should be probabilistic. So the point is the idea that complex physical, biological, or sociological system can be exactly described by a formula. This is a very clearly, the point is it is absurd because complex physical system cannot be defined through the equations directly. We can have the top level equation, but later on we need to add the approximation. So models provide useful approximation because it is not possible. In the beginning itself, we can say this is the system in terms of equations. Okay. So the last point is very important. We need to remember models are not wrong. All models are wrong. In the beginning itself, we assume. But practical question is how wrong do they have to be not to be useful? Make sure model will be useful, but we cannot say it is exactly replica of our physical system. So a model need to be true to be useful. This is the main objective behind model-driven process. Yes. Now, so why I was talking with respect to model and determinism for that? Because whatever the software we design, software is itself a model, and it look like in the physical system, like in the chip, we have got our software codes. So this coding part is the model, and we have embedded into the physical hardware. So it's a model itself. Software is also a model. So that's why in the beginning, so if we think through the reverse engineering, whatever the program in the computer system, if we break down into the coding part, so this is the model. So we need to understand how things are connected here. Next. So this is one example. Another example is in the VLSI domain, whatever the physical system or chip we are using. So behind that, it is a great model, like a RISC-V model processor for that. So we have a great coding part that is to be done. It is actually model, and in the software generally the things happen into the determinism form. Because whatever the input we give, we expect this output. Next. Another is the digital logic. Whatever the gate or synchronous and asynchronous combination we create, that is the model. But at the end, in the chip level, we create as a physical system. So first we need to realize realize what is model part, and then later on design and then analysis, that is to be actually going into the physical system itself. So synchronous digital logic is also a deterministic model. So lot of information or processing equipment what we are using nowadays, these are deterministic in sense. Like in mobile we have a lot of chips, and these chips are actually nothing but model and softwares. These are deterministic in nature. But when we have a different kind of physical process where uncertainty is inevitable, then uncertainty to be considered while designing model equation. Next. This is another example, like in electrical domain, we have a motor and then a model equation we frame. This is also in deterministic format. But when we use such kind of system in actual practical realization, then all kind of uncertainty we should consider. Next. Okay. So now where major problem comes into the picture. So here combination of deterministic model are actually non-deterministic. How it is coming non-deterministic? Because we do not know exact scheduling time, exact synchronization between two different physical components. Through software, we are actually controlling our motor, and here both are actually deterministic in the standalone point of view. But when we are talking in integrated format, then both will behave as a non-deterministic one. So, in the beginning itself, as we have discussed, component-wise designing will not work into the CPS. We need to think through the integrated manner. Yeah, so the same again, abstraction layer help in the designing part, like teams are divided, and within a team we have a different resource person. They will be acting into the different layers, and at the end they try to collate the information. But generally such kind of abstraction layer actually hinders the CP cyber physical system design at the end. So abstraction layer will not work here. We need to continuous assess with the different team and feedback and re-collaborate. Then only real cyber physical system will be designed. Yes. So this is the abstraction layer. If we follow abstraction layer, then it will be totally failed in the cyber physical, because every abstraction layer has a field for the aircraft designer. Because while designing aircraft as a cyber physical system, it was really challenging task, and they tried every way in terms of abstraction layers. It was totally failed. Nowadays, it's a fly-wire kind of things, totally commanded by the pilot, and he takes the instruction for our ATC towers, and then they can be simply handle the whole aircraft. Yeah, next. Okay, so here we need to raise the abstraction labels. I mean, we need to mix the labels and communicate with each layer to understand the flow of information and further processing. So this is the great example where abstraction layer is not work in actual real world for the cyber physical system in flight, where just fly by wire, aircraft, a computer control the plane, and just pilot mediates the whole process. That's it. And instruction came from the ATC tower. That's it. So here there is no abstraction like the other team is working and then integrating without any feedback from each other. So it is really difficult. So we need to understand abstraction layer should be removed while designing CPS. As I told, higher abstraction will lead really probability. So we need to make sure if we are following abstraction layer kind of architecture to design any physical model, then consider it should be very interactive and feedback kind of abstraction layer. Okay, so we are coming back to our original question, whether it should be determinism or will work really into the application with respect to the CSP. So CS cyber physical system application operate in an intrinsically non-deterministic world, but that doesn't mean it hinders to design a model in a deterministic. Because individual model are deterministic, but that connection to be happen properly, and after connection it work as a non-deterministic. Yeah, next. So here for a model to be useful, it is necessary, that is not sufficient condition, but it is necessary to be able to construct a faithful physical realization. This is the only objective while modeling part. And if we take the determinism path while designing any model. So in engineering, model fidelity is a two-way street that never happen actually. But the point is, it is necessary to be able to construct a faithful realization. That is to be main objective behind model building. Okay, so again the question whether deterministic or non-deterministic. So the question is whether we can build a cyber-physical system whose behavior matches that of a deterministic model with a high probability. So at the end we are reaching towards our non-determinism. At the end we are talking with respect to high probability, like a fidelity, how it is operating into the physical. So if we are taking model building, then these two parameters to be very carefully, resilience and adaptability. So deterministic model do not eliminate need for robust fault tolerant design. So that is separate part actually, but first is the model design. And later on, if it is actually producing whatever we are expecting as a target value, then these factors to be considered, whether it is a robust and fault tolerant or not. Robust means if any uncertainty is coming while operation, our model is able to handle. So that is robustness. And another is the fault tolerant. If fault is coming, then it is able to rectify and correct that. So that is a fault tolerant element. So when we adopt such kind of design into the picture, then automatically deterministic model leads for the non-determinism portion. Next. So what we were talking, initially we were talking model driven system design. Now we can use the data driven system design. What happens? So model driven system design works where physical system is existed from last many years actually. Suppose we take example a power plant. Power plant are running from a lot of years. Now every component is having good physical information and physics behind every component. We know actually. So for such system, model based design is easy. But now if we talking latest technology like blockchain based application, augmented reality, and kind of anti-drone technology, not drone related, anti-drone, then also thus in such cases data driven approach will work very well. So this is the also designing part, how to design the data driven based system for the cyber physics. So how happen? Here data is a core asset. So we should know the historical data, and based on that historical data actually we try to model every component of the physical process and computational portions. So it offers a lot of advantages, like it will be model free intelligence, it is adaptive behavior, like whatever we use nowadays in industry 4.0, that is digital twin kind of information. So digital twin is having adaptive behavior. If whatever coming as a process parameter, if there is any fault, it try to rectify that and adopt the actual process. Feedback enhanced design, we can design a lot of control mechanism using the data driven approach. And in the data driven model, scalability and generalization is an easy way. So nowadays the example for the cyber physical system, this is the data driven base, smart manufacturing, autonomous vehicles, predictive maintenance, in industrial IoT based. So nowadays my research group is working with the data driven application for the nuclear power plant. So Government of India is proposing like space that is still not open for all, but nuclear domain is now open for all. They are trying to build a micro modular reactor. Nowadays we have a simple nuclear power plant, generally 500 megawatt, but government is expecting let design for 20 megawatt. 50 megawatt kind of reactor and operates through the truck. Like we load the reactor in the truck and we can provide an emergency backup anywhere. It may be Navy ships or any accident areas or any suppose attack happen and all of a sudden blackout, that we can use such kind of plant. And it is generally in close to renewable energy. So here what we are proposing digital twin cyber physical system for the nuclear power plant. So right side we are having set up equation. And these are well defined for the power plant. So by equation we can design the deterministic model of the system. But at the end, for the digital twin, it is really difficult to follow the equation because process may change as per the requirement, as per the application. So if we have adaptability for the real time situation, then such kind of model would be grateful. So for that, we are generating lot of data to such equations by putting different conditions, different operating points, different fault conditions, and based on that, we are training our models. Yeah, next. So for that, we have concluded this work. We have designed LSTM, long short-term memory-based neural network-based to replicate the whole nuclear power plant. Okay, so here we have targeted two major sensors. One is the neutron flux sensor, another is the temperature sensor. Because in any nuclear power plant, temperature and neutron flux to be maintained very carefully. And generally, in power plant, temperature sensor are close to around 200 plus temperature sensor. And similarly, in array in circular way, close to 500 neutron flux sensor. So we need to manage such huge information to be modeled in our data-driven decision making. So what we are doing, we are generating a lot of data set through equations, through different conditions, through different temporal and spatial coordinates, the location of the sensor, and then we are feeding into our deep neural network. That is a long short-term memory network. Because the information is temporal. Temporal means, like suppose we are starting a plant, so from 0% there will be power, and we are reaching 10%, 20% like this. So every time instant we are need to be memorized in the system. So LSTM model is chosen. And simultaneously we are adding the fault tolerant mechanism also in that. The next. So for the simulation, we have done very interesting simulation. Like suppose in the temperature sensor and flux sensor, there is an incipient fault. Like a fault can be three types: abrupt, incipient, and intermittent. Abrupt can be observable through the operator eyes directly because magnitude will change suddenly. But incipient happen over time. So for incipient fault, we are adding into the actual sensor data, and then we are trying to estimate that fault profile through our whatever the data driven model we have developed using LSTM, group of LSTMs. Okay. So in the right side, if we see this broken yellow line, is actually trying to estimate actual fault profile. So through the data driven, we are able to predict whatever the fault is mixed into the actual sensor reading, and later on we are correcting that information by subtracting that fault amount through the actual value. So what happened here, based on the data driven approach, we are actually rectifying in the real time manner. So we need not to stop the plant and then plug out the sensor and then recalibrate and then put back again. So we are doing into the real time mode, and it is adopting actual process, and it is fault tolerant in way. So such data driven modeling is really grateful for any cyber physical system to be realized. So these are the results in terms of the fault correction. So if we see, the green one is the corrected and the red one is the measured. Measure is coming due to the fault. Fault is not in the process, fault in the sensor itself. Because if we install the new sensor, that is fine, but after a few days, after a few months, there will be degradation happen because it is in harsh condition. So due to that, reading is getting deviated. So from the previous, we have estimated the fault and then corrected back to the original reading. Now here, if we see the power and the temperature is not in, like range is very low. But for temperature it is important because whatever the moderator or coolant we are having to the nuclear power plant, temperature to maintain very carefully. Otherwise what happens, it may be in the gaseous format. So equilibrium to be happen with the three phases of whatever the material we are using as a moderator. So the point is every minute detail to be considered with respect to the physical process while designing cyber physical system. Then only we can involve our cyber with communication for a physical system. Then automatically it will complete cyber physical system. So any physical process can be observed through the sensor and controlled by actuator. So as here mentioned, a sensor is a device that measures a physical quantity directly, input and read from the physical one, and actuator is a device that modifies the physical quantity. I mean, it actually changes the operation of the plant, accordingly reading will change. So output and write to the physical one. And sensor and actuator group is actually able to make the closed loop system. So at the end what we are looking, we are providing a command and it is reaching to the system through actuator, and after that we are measuring the value again and coming back to our computational platform and it is going back again. This complete loop is actually done through the sensor and actuator system in a between computation that create a cyber network. So then we call as a cyber physical. So these are the list of sensors, how we bridge the gap between the cyber and the physical through sensor and actuator, cameras, accelerometer, gyroscope, strain gauges. So every sensor information to be processed very carefully before using that sensor. And similarly with respect to the actuator, because the modeling issue will be considered while addition of any sensor, like the physical dynamics, noise, bias, sampling, interaction, all these parameters. Next. So this is the sensor rich car as we have discussed in the beginning itself. So what kind of sensor it is having actually? GPS, lidar, video camera, ultrasonic sensor, odometry, central computer, radar sensor. Okay. So these sensors are actually interacting with the physical world. And on board computation, I mean with the car, whatever the embedded system we have, it processes the whole information coming via network, it may be wireless or wired communication, to process the information of the sensor and again back giving the information for the actuations. Okay. So we are covering a lot of information like based on lane departure, parking assistant, self parking, side impact, blind spot detection. So we can think any application with respect to this smart rich car, but we need to understand which sensor to be utilized and how actuation to be done, and for that what kind of onboard processing to be done. So this is the whole idea behind it. So at the end, if we are looking for the model driven design or data driven design, so we should know the basics behind sensor model, how it can be represented in terms of equation. Like to understand the physics behind sensor, that is different part. Later on, next layer to be go with the sensor modeling, whether it's a linear affine function or total non-linear relation between the physical quantity what we are measuring and sensor response. So these parameters to be taken care accordingly, because at the end the modeling of the equation, which is actually replicating our sensor system, will specify sensitivity and measurement change when the physical quantity changes. So these two parameters will be coming to the picture again. So precision and accuracy, as we know, how close the two major values. Like if we are repeating the experiment, how close the value we are getting, that is precision, and for the accuracy, how close we are actually target value. So these two parameters will decide the selection of sensor. Sometimes if we are looking low cost design of a cyber physical system, then accordingly precision and accuracy can be considered. Similarly, so these are the component wise explanation I am providing, because at the end we are trying to interact with the physical system. So when we are interacting with the physical system, then sensor is providing continuous information, but our computation will happen in the digital mode. So for that, analog to digital converter to be installed. Now we have a lot of category with respect to analog to digital converter. So we need to choose what kind of accuracy we are looking while conversion, what kind of sampling we are expecting from this ATC. Now again, whatever information we have digital, after processing we need to go back to the physical, that is to be converted into analog format. Then this is the portion we need to use the tag, and accordingly we need to select the tag if as per the application. Next. Zoom in out. So now we'll talk about the one modeling tool that we can use, that is Kalman filter. Actually it provides a great estimate for the next time instant by having the present information. It is a probabilistic kind of filter, and initially how, just a brief history, when Apollo mission was launched, then US started exploration, like who will design the trajectory for the system, whatever satellite we are launching, who will decide trajectory. So this project was awarded, like a lot of universities have been searched, no one was coming forward because it is really difficult. We do not know any next information, but we need to reach there. So for that, the Kalman scientist came forward. He told, I will design an algorithm. So he designed an algorithm. How it is? Like at present, whatever value we have, based on that, next future value will be predicted based on the uncertainty only. So like nowadays in the data science happen through the data information, but here through the equations. By equation we generate the data and next information we create. So here if we see again that big picture with respect to connection of the cyber physical system, we have physical plant, sensor, actuator, computational platform and network connection. So here a lot of comments are there: unknown execution time, part failure, physical noise, model visibility. These are actually probabilistic parameter come into the picture while designing any real system. So to consider such information, we need to add the uncertainty in our original model design. So here what we are assuming, whatever sensor is getting measured, that is random variable, and that can be described through any probability density function. And measurement mean we are taking as an expected value of the random variable. Like suppose whatever, if we are measuring suppose temperature at one time instant, it may be T1 degree Celsius, so next time instant it is T2 degrees Celsius. So based on that we create a probability density function, and mean value we are taking as a measurement. So this is the basic concept, and if there is any shift that is taken as the error from the mean value. Next. Okay, so yeah, next please.
Next.
So if we want to create a feedback system based on the measurement and for the actuation, then Kalman filter family based algorithm can be utilized. It is having for linear system, non-linear system, Gaussian noise, non-Gaussian noise, whatever. So we have a big family for such kind of filter. We call it a probabilistic filter. So for that we create any system equation. Based on that we add the model uncertainty and measurement noise and the system noise into the consideration, and based on that we optimally estimate next state. Next. Next. Next.
Next.
Yeah, thank you. we see the system, it is in complete loop. So generally we use nowadays we use like we using the PID controller, now the data driven controller, optimal controller. For that actually, so suppose we do not know the measurement for the next time instant, so accordingly we try to estimate based on the Kalman filter to the next estimate that error to be fed into the controller, and accordingly the control gain will be proportional change, and then plant will be controlled to check the dynamics. So this can be act as an observer while designing any Kalman filter based controlling mechanism. Next. Yes, so here how it actually converges. So the first block is representing car dynamics. If we want to control the movement for the car, so we know the car dynamics, and based on that we have generated a model. Dynamics can is the true one, and model is the replicated what we are trying. So on that we have added this WK, that is noise in the in the process, and nu is the measurement noise. So after that we are taking the measurement, and next value we are predicting, then we are trying to add the new measurement and then predicting new value, then later on we are converging the state. So we are choosing optimally stable state that is telling this is the next measurement or true measurement. So it can act as a filter and predictor or the smoother. Three portion can be taken care of. Yeah. So in this probabilistic filter, two processes involves. One is the time update, and other is the measurement update. Time update will tell what will be the next value. Measurement update is actually correction of the previous value. Whatever information we have taken from the measurement, that is fed back again, and measurement will be corrected, and the next prediction will happen. So this is the whole process behind the probabilistic filtering. Yeah, next. Yeah, next. Yeah, next. 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 The 2D model we'll see next. This is 1D model. Here. Yeah. So airplane constant acceleration model. Suppose we are looking to control through the Kalman filter. So small flight sign is in the coordinate system. So the point is what will be the next location for the flight. So for that we need to understand what will be the state, what are the control parameter, like that can be given through the actuator, and what kind of governing equation is following that path. And based on that we are actually trying to model the whole system. So simple equation, Newtonian equation, and based on that we have a transition matrix, like how state is transferring from one time domain to another instant, and control matrix, like what measurement on what way we are getting measured. So this is the picture actually telling when we are trying to model a system. Based on the model we need to identify states, control vector, measurement vector, and the transition vector matrix based on which states are going to be communicated. Yeah, next. 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 Yeah. Here also. Like another equation is with respect to the pendulum. It's a very classical problem in the control system. Inverted pendulum, and we need to control the motion of the pendulum or rotation of the pendulum. Okay. So this is the simple governing equation in the state space format, and based on that we can determine the states and the dynamics, and accordingly in the matrix format, and then we can use the probabilistic filter to estimate the next value of the measurement or the state. Next. So it can be taken care for the nonlinear system also. It is a different group of category like EKF, extended Kalman filter, unscented Kalman filter, particle filter, bootstrap particle filter. Yeah. So here if we assume system is non-linear, so first we find the nonlinear dynamics. Later on we linearize through any standard mechanism like Newton-Raphson or the Taylor series. How much order we can handle in the nonlinear. Here unscented Kalman filter take care non-linearity in a great manner in terms of 3 degree or 5 degree. Non-linearity can be taken care because it's consider the data samples and regenerate the distribution and then resamples measurement like this. So in the particle filter we can handle more non-linearity with non-Gaussian noises. So this kind of probabilistic filter we can choose based on the physical observation. So if we have a such system under observation which is highly non-linear in the nature and highly non-Gaussian noise are inbuilt in the process, then we can choose the particle filter. Next. So it's a broad comparison when different state estimation or probabilistic filter can be utilized. So these estimators are being used to control the whole process. Whatever information we are getting, that is from the sensor and processing by a control law, and control law is done through the state estimator, and that control law is generating the control signal for the actuator. Next. So we have application, whatever the probabilistic filter I have listed out in SART actually. These are great application in GPS tracking. Nowadays we are using this application. Whatever mission we are launching through the ISRO in our country, here probabilistic filters are the core computation point. Okay. So they actually predict the next stage, and as we have seen in the Chandrayaan landing, landing was done through this only probabilistic filter. Because every time we need to track the path and then provide the feedback. So this is a very important algorithm which is actually working as a core computational algorithm for many applications like wind tracking, weather forecasting, nowadays whatever weather forecasting based on that only. Because lot of uncertainty with the weather forecasting. Still, we are trying to build the data-driven model, but in sample Kalman filter is still superior compared to other. Another application now ADAS, what we are using, GPS tracking. Next. Okay, so at the end, what we have discussed now, different definitions of the CPS components, cyber physical system components. Core component, what will be like physical plant is the main heart in the CPS, and then sensor actuators are the main component which is going to control the plant, and the computational platform. Design roadmap we have discussed, it should be through pass through the model, design and analysis. We can choose any way to design, it may be data driven or model driven design. Now we need to understand how hardware to be interface. Here I have provided an example Raspberry Pi. They are a processor based embedded system that can be used for the play and the research kind of applications. Modeling principle to be followed very carefully, whether it may be deterministic but add probabilism next stage. Application, it's a huge and tremendous application, and in the CPS almost we are reaching into the plateau of productivity into the hype cycle. That's all from my side. Thank you. Any question from you? Yeah.
We are dealing with more deterministic models, and we are combining these. The outcome we are getting non-deterministic because certain type of non-identity. Will only time play the role or other factors?
Other factor will also be like time is the major contributing factor, because if we are dealing information or communication between two components, then automatically other environmental factor will be added.
Like temperature, pressure.
Not exactly temperature pressure, but suppose we are transferring information from T time, but it is reaching at the T2 time. So in between, maybe other environment, like if the system is in the noisy environment, then different kind of noise will be added in between. Now, if next component is reached to state itself. But we are actually receiving signal from the previous state. So there is a delay, like scheduling problem may happen. So different kind of consideration to be taken care while connecting the system.
One more thing that the higher abstraction problems.
Yeah, so higher abstraction means suppose we are designing let's say anti-drone technology. Okay. The target is if any drone is coming or any explosives coming, let's break down that. Okay. So but for that we have selected lot of teams. Someone is expert in the aerospace, someone is expert in the electronics domain, someone is expert in the mechanical. So within a mechanical, again one guy will come, I will create such kind of material and flexible component. So this is one kind of abstraction or layer. So the point is, if we give a lot of freedom to every individual member and the team, then it will create a lot of abstraction. Because everybody is thinking in its zone abstract format. So here we need to intermix and take continuous feedback and let adopt what we are looking for. Then automatically this layer can be drawn.
Sir, can you name the automotive company which is in Bhopal?
Yes, I will send the detail. Actually, we are targeting also with them. Research.